together with my colleague, Professor Deborah Crone, I'd like to welcome you to the Renaissance Visual and Material Culture Seminar that we co-organise. The Bard Graduate Centre is, of course, dedicated to the study of the material world, and increasingly the material sciences have become more and more important to our curriculum, as embodied by Jen Maas, my colleague, but also by, for instance, the Mellon-funded ongoing research projects, Cultures of Conservation, whose ambition really is to marry the knowledge of conservators with those of the humanities and social sciences in a series of ongoing projects. And so it's a tremendous pleasure to welcome tonight's speaker, Professor Robert Erdmann, who is Professor of Conservation Science in the University of Amsterdam, in the Faculties of Science and Humanities, and is also the Senior Scientist in the Rijksmuseum Conservation Department. Professor Erdmann received his PhD from the University of Arizona in 2006, but before this, he had started his own company, or his own enterprise, a science and engineering software company that worked extensively on, to me, the arcane topics of solidification and multi-scale transport modeling at the Sandia National Laboratories. This will mean, I think, more to people in the audience than to me. But he subsequently joined the faculty at the University of Arizona in the departments of mathematics, applied mathematics, and the Department of Materials Science and Engineering, where he became eventually associate professor, and where he worked on, again, the rather, to me, arcane topics of multi-scale material process modeling and image processing for cultural heritage. This is where he began his work on objects of cultural heritage, I believe. A residency in 2013 as a fellow at the Netherlands Institute for Advanced Study led him to move permanently to Amsterdam in 2014, where he took up his positions at the University of Amsterdam and at the Rijksmuseum, and has focused full-time now on combining materials science and computer science, with the ambition, really, as we will see tonight, of providing the most extraordinary access, actually, to these objects of cultural heritage that the Rijksmuseum really embodies. And he's been at the absolute forefront of combining the most sort of, I suppose, contemporary imaging techniques of conservators with digital technology of to me, a mind-boggling complexity and interest, applying essentially techniques of artificial intelligence and facial recognition techniques to the objects and works in the Rijksmuseum. I will not say any more, other than that the fruits of his investigations are probably most accessible to us today in the website for the Hieronymus Bosch Research and Conservation Project, which was a collaborative project which sought to examine and to compile a kind of investigative database, I would say, of the entire oeuvre of Hieronymus Bosch. For this, he received the Europa Nostra Award, Grand Prix, the highest prize for cultural heritage in the European Union. He's also the inventor of the curtain viewer visualization technique, which I believe we'll hear about this evening. And he's worked extensively on automated canvas analysis for easel paintings. Much more of this, I think, to come. And so, without more ado, I'd like to welcome Professor Erdmann. The title of his talk is The Secret Life of Art, Data Science for Art History and Art Conservation. Welcome, Dr. Erdmann.
Well, thank you, Andrew, and thank you to the Bard Graduate Center for having me here, and thanks to all of you for coming. And of course, my work relies on the work of large teams of people to gather the vast quantities of data that end up going into all these visualizations. So I would be remiss if I didn't thank all of the photographers and conservators and art historians with whom I work at the Rijksmuseum and museums across the world. So, yes, tonight, buckle your seatbelts. This is going to be a fast, high-level overview of a sort of 10-year project. I'm on year 7 of a 10-year plan to try to bring modern advances in imaging technology, material science at multiple scales, human perceptual psychology, visualization technologies, and data science to help the world access, preserve, and understand its cultural heritage. So I hope that what you take away from this is a sense of the possibilities that exist, a sense that we haven't even begun to really tap the potential of bringing together computers and data and the internet to help the world access, preserve, and understand its cultural heritage. And also, when I'm done, I'll show you how simple all of these things really are, in the sense that they rely on a small set of tools that are designed carefully to interoperate with each other. So, to begin. This is a small painting. It's 48 centimeters tall from Hieronymus Bosch. This is in Madrid, and this is John the Baptist in the wilderness. He's meditating, and he's pointing his finger here at the Lamb of God. And hopefully when you look at this, it looks like this is a single photograph. But the first aspect of my work is to gather as much data as we can possibly collect about any given artwork that we're studying, and to fuse that data together. So what that means is, in this particular case, this is a photograph, this is an assembly that was made around 2014 or 13, if memory serves. So this is a bit dated by now. This is several dozen 60 megapixel photos that have been stitched together in such a way that it respects human perceptual psychology, so that we don't notice any flaws that may be present. The lens distortion that's due to the camera is corrected. Any lighting differences from the left to the right side are corrected. And ultimately, this is stitched together into something like a 5 gigapixel, so 5 billion pixel image of this small painting. In light of the fact that ultimately I'm going to collect a huge amount of data, and I want to do analysis on it, as I'll describe in a moment, and ultimately deliver it to non-computer professionals, so art conservators, curators, art historians, and the general public. Everything that I do is internet-based, and in fact this computer is a Chromebook, so this only runs a browser. So this is a way of practicing the software engineering concept of dog fooding, and that is, if you want to make sure you make good quality dog food, you eat your own dog food. So, so I'm eating my own dog food here, and if anything goes wrong, that's why, because I'm sort of living on the edge here. But so this is a technology that's called the curtain viewer, and this allows me to zoom in on very large images in a very seamless way. Here I'm zooming in on a little mark, which is actually a ballpoint pen mark, where someone was giving a tour and with a ballpoint pen, and they pointed to the Lamb of God. Oh, and here's the Lamb of God. So when we told the museum about this is owned by the Museo Lazzaro Galdeano in Madrid. They said, no one's ever noticed this, so we'll just leave it. So here you see that there's John the Baptist, and there's this strange fruit. So the next aspect of data fusion is that we don't just use a single kind of imaging. In this case, we've also used an infrared reflectography camera called an OSIRIS camera. This is operating at around 750 nanometers wavelength of light. And what this means is that the light scatters dramatically less, and therefore is able to move through this translucent binding medium, the oil, which is dried, probably linseed oil, to let us see what's behind it. And so that means that we have an assembly of images from a visible camera, and also an assembly of images from a camera with a different set of optics, different lens, different resolution, and so on. And so we have to stitch all those, but we have to do it in such a way that we can perfectly align the two, which is called registration. So when we do that, then we would find something like this. So here is an infrared reflectogram of the painting, and as you can see, this has a nice surprise, which is that there is a donor, the bottom of which has been cut off apparently, who's kneeling in prayer next to his name saint. So this is a common practice at this time. This was painted more than 500 years ago. And the practice was that you would commission a painting from a well-known painter if you were a rich aristocrat, and you would ask to be painted in a very pious position next to your name saint. So this is John the Baptist, so his name is John. And apparently when the painting was finished, he didn't pay Bosch, and so Bosch turned him into a vegetable. But this is also highlighting a feature of human perceptual psychology, and this is that we have extremely limited visual memory, about half a second of visual memory. So if I would ask you to study this very carefully and try to remember every single detail that you see in this, and I'll wait for a few seconds. Now, I'm going to ask you how many of his toes are curled. Probably not many people can do that because we have a general sense of the composition, but the individual details are lost. So that means that when I switch back and forth from here to here, this is hard to keep track of what's the same and what's different. Okay, so the obvious next thing to do would be to display images side by side. And now I'm additionally displaying two more kinds of images. Down here in the bottom right, this is an infrared photo. So this is where we've taken a regular high-resolution camera and we've removed the infrared blocking filter that's present in every digital camera, and we've added a visible light blocking filter to the front of the lens so that we can photograph at wavelengths of around 1100 nanometers. So that's down here. And over here is a radiograph. So rather than bouncing electromagnetic radiation off the painting and capturing it on the same side, instead there's a film that's placed behind the painting, and then we're measuring the radio opacity. But still, this is like the newspaper game where you have two cartoons that are identical except for 10 differences, and they're placed side by side, and you have to bounce back and forth and see what the differences are. That's challenging because of something called context switching. So when you are looking at an image and you establish where everything is relative to everything else, and then you switch to looking at another image, even if it's over there, it takes more than half a second to get there and to reestablish your context and to think about the mappings between the two, which means that by the time you get there, you've lost what you had from before because you've forced a context switch. So in 2012, I tried to solve this problem because I wanted to make a tool that would help people compare images. So I came up with what I call the curtain mode. And by now it's probably familiar to a lot of people, but the idea is that rather than forcing context switching, I allow the user to focus at one particular location, and then I can switch the image out from under their view so that the context switch is minimal, like so. So for example, here you can see that there's a tree which was present in the original, and that when the tree got painted over, actually some of the branches are retained. So in terms of studying whether it was in fact Bosch who painted this over or someone later, we now have two obvious layers of the painting that we can use to compare. Similarly, this kind of technique can help me to understand the conservation history. Here you have a very obvious example of an Italian restoration technique called trateggio. So this is a vertical hatching that's intentionally meant to signal that this is not the original work of the master, that this is a restoration. And of course, when you zoom out, you probably don't see that. And that's the intent, that when you're up close, you see the striation, and when you're far away, you don't. But if you look at the infrared photo, it really does a great job of highlighting that. Also, what you might not have noticed, were it not for the ability to see this photo, is that we have some additional areas here and here and here, which are also restored, but which do not employ this Strategio technique. And in fact, using this high-resolution image, now that I zoom in, you can definitely see the colors are a bit different, and the craquelure is missing. So this is different as well. Using this kind of infrared reflectography, I can also look behind and see any underdrawings. So here's a beautiful underdrawing corresponding to that. And an additional way to compare images is to fade from one image to the next. So here you can see I can fade in a little bit, or I can fade in just a little bit of the infrared so I can see the correspondence. And now that you know where the head is, you can see that actually the paint has thinned to some degree over time so that it's now slightly translucent, and I can actually make out that boundary a little bit where the head is. So, so that's the basic curtain viewer technique, and virtually everything else that I'm going to show you today is also using the curtain viewer, except for two exceptions. So, so you can see that in the project for Bosch, which ended in 2016, we had at the time taken the world's highest resolution photographs, and those were 1250 dpi or 20 micrometers. I prefer the resolution to be specified in terms of spacing. And for those of you who are not familiar with what that means, if I say a photo has a resolution of 20 micrometers, what that means is you have two worlds. You have the world of the image, which is pixel-based, and it does not have an inherent size. It has some number of pixels wide and some number of pixels tall, but it doesn't have a physical reality. And then you have the object that I've photographed, or that the photographers have photographed in this case, and that, of course, has an actual physical size. Now, if you're photographing a flat object, a two-dimensional object, then there is a one-to-one correspondence between every pixel in the image and a location on the painting. And furthermore, if you photographed at right angles to the flat object, when you move one pixel to the right in the image, you've moved some fixed distance to the right in the actual real world. And so when I move one pixel to the right in this image, I'm moving 20 micrometers to the right in the real world. And to give you a sense of what 20 micrometers is, a human hair, well, it varies, but the average human hair is something like 60 micrometers wide. So a human hair would require 3 pixels to capture in this image. So camera technology gets better, and I get a little bit more insane. So this now is more up to date. This is a Rembrandt drawing. This is of Saskia, or at least it's said to be of Saskia, though some people disagree because they say, so Saskia was Rembrandt's wife. They say that Saskia would never dress like a peasant like this, but maybe she dressed up for him to draw her. In any case, this is a 14 centimeter tall drawing, and that is 5.5 inches tall. And this has been imaged using a state-of-the-art Hasselblad camera that gives me 3.5 micrometers resolution. So that means I move 1 pixel to the right in this image, and I've moved 3.5 micrometers to the right in the real world. And to give you a sense of that, a human red blood cell is 8 micrometers wide. So what can you do with an image like that? Oh, and I've left on the edges because this is actually an array of 4x4 400 megapixel photos that, again, have been stitched together. So when I zoom in at this level, you can see that there's a sort of interesting pattern of white marking here. It's almost like it's white out. You can see it here in her eyes and on her chin. And you can see that she's holding something which is hard to make out because it's this sort of dark vertical area. Now this would already be considered a fairly high resolution image, but with this technology, I can zoom in and in and in and in and in, down to the layer down to the level that I'm seeing here, where you can see that in fact this dark area is actually a paste which has dried and cracked, and it's sucked up the color of the iron gall ink below it. Though these high parts are probably ultimately going to discolor, but these are the tallest portions, and so they've not yet been affected by the color. You can also see, if I just zoom into the paper, that now I can make out the individual linen fibers, because this predates making paper out of trees. This is where you would take carefully sorted white rags made of linen and make paper out of that. So I can see the inner wall and the outer wall of the linen fibers. I can see areas where there is a kind of perhaps a corrosion product here. I can see evidence. Notice that there is a statistical tendency of these fibers, the darker ones, to be vertically aligned. So I can make out the direction in which the shaking was happening during the making of the paper, because when the fibers were locked in, they were moving in the vertical direction. So in terms of the drawing as a physical object which has a materiality, this kind of imaging lets you see things that you couldn't dream of seeing otherwise. But this is just a photograph of the front. So what if we think about trying to combine additional imaging modalities for this drawing? Well, that's what I'm about to show you. So here we have the drawing as seen from the front. Now, if you were to take the drawing and turn it over, that could be interesting, because you can see that there are areas here and so on, where he applied this whiteout, we think, where probably the ink was so dark that he wanted to lighten it up. So if we were to turn the drawing over, we might see where it's saturated through to the back. Now, to make a comparison with the front, it would be convenient if, when we flipped it over, we also do a mirror and use a neural network to very precisely align the image of the back with the image of the front. And so if we do that, we see this. So here's the front and the back. And actually, you'll see now in mirror form the collector's mark from the Rijksmuseum, because this is owned by the Rijksmuseum. And you can see the areas here where we've really saturated back to the back. And in fact, you can see here some drips, possibly Rembrandt's tears, where they have transported ink from the front to the back. But if you work with drawings, you'll also know that a transmitted light image is an interesting thing to have. This is something that would be typical if you're looking for a watermark. So here we've taken the drawing and we've put it on a light table and imaged that, and then subtracted the exact brightness pattern from the table itself, because it's not perfectly uniform. And if we do that, you can see here that the collector's mark from the back is blurry because there's scattering of light. So now the light path is, the light is going from the back to the front. Now we can also flip the drawing over so it's face down and do a transmitted light from the front to the back of the exact same area, and now we get this. And here you see that the drawing is sharp and the collector's, the drawing is fuzzy and the collector's mark is sharp. And ultimately we can combine all of these and take a kind of virtual journey where we take the back of the drawing and move it forward at the same time as we're taking the front of the drawing and moving it backwards, so we can kind of turn the drawing inside out. So I have a PhD student who's working on the problem that the suspicion that since I can tell that here the drawing is close to me and the stamp is far away because the drawing is sharp and the stamp is blurry, whereas here the stamp is close to me and the drawing is far away because the stamp is sharp and the drawing is blurry, that by having a computer meticulously analyze the sharpness of every stroke, that I can get a sense of how deep the stroke penetrates into the drawing and perhaps create what we call a ductus diagram, in which we would reconstruct the sequence of strokes that Rembrandt made in creating the drawing. It's also interesting to note that when we switch from this view to the transmitted light view, the whiteout sort of goes away. Of course, you can also see the chain lines and the laid lines. Here's a chain line going across. Here's another chain line, and of course the laid lines are vertical here. So, this experiment using this shockingly high-resolution digital photography led us to think, all right, well, maybe we should do this for the night watch. As you may know, we're in the middle of Operation Night Watch, in which we have built a glass box around the painting in situ in the Hall of Honor in the Rijksmuseum. We're in the middle of a 10-month research campaign, after which we will learn enough about the painting to know what sort of conservation treatment is needed, and then there will be a conservation treatment of unknown duration. So during this campaign, we are going to be photographing the entire painting at 4.75 micrometer resolution. And the painting is around 4.5 meters wide. We have pixels of around 4.5 micrometers wide. So that means that when we take our 11,800 separate 400 megapixel photos and stitch them all together, we're going to have a single image of the painting that's 1 million pixels wide, approximately 768,000 pixels tall, 4.5 terabytes. But that's just one imaging technique. We're also going to use imaging spectroscopy at 600 different wavelengths. We're going to use infrared reflectography, UV-induced visible fluorescence, optical coherence tomography, 3D scans from TU Delft, macro Xray fluorescence, which we've already done, and ultimately we're going to collect 600 terabytes of data for this one painting. So this is, in a way, kind of a moonshot for us. So before we really dive into that, we decided, well, let's start smaller. So this, as I don't know how well you know the Night Watch, but this is a copy of the Night Watch. This is not nearly as good as the Night Watch. The Night Watch is 4.5 meters wide. This is 80 centimeters wide. And this is a copy that was made, it is believed, when the painting still had not been cut down. So the actual Night Watch ends here, and all of this is missing, and the top has been cut off, and so on. So we decided to try to use this new imaging technique, 4.75 micrometer resolution, to image this painting. And we used our old technique, which is 20 micrometer resolution, which was also state-of-the-art, I believe. And so this is a comparison. And for the comparison here, I will also illustrate another feature of this technology, and that feature is that I can record my actions as I explore this pair, and then play them back in a smooth way. So I'm going to attempt that here. So I'm going to turn on the recorder, and then I'm going to begin recording. Now the image on the right is the high resolution image, and the image on the left is using our old imaging technique. So I'm going to sort of pan around across some of these, to me, beautiful details. And I'm going to zoom out a little bit. And zoom out a little bit more. Okay, so I've stopped the recording. I'm going to put this on a looping mode, And then I'm going to sort of steady cam this and play it back. So now the viewer is playing back the sequence that I took when I zoomed into this pair of images. And lest you think that this is just like a screen grab, it's not, because at any moment I can pause this and I can go exploring the painting, and then I can resume it and it will take me back on my journey. In fact, there is an entire editor which I could use to sort of cut and paste and do sort of standard movie editing things. But the point here is that this is not just the cult of resolution, because I hope you can see, especially in this detail, which for me, if you told me that this was a photo of the surface of Jupiter, I would not necessarily question. You can see that the difference is that in this image, which is 20 micrometer resolution or 1250 dpi, I cannot make out the individual paint pigment particles, whereas on the image on the right, which is 5340 dpi, I can. So in terms of this being a material object that has secrets about, yeah, here I can see smalt particles quite beautifully and so on. It has secrets about how it was made, just visible as long as I'm looking close enough. What pigments were used, what is the sequence, how finely were they ground, what was the direction of the brush stroke, and so on. I will be able to see that with the image on the right, but not the image on the left. And so we're using the right technology to image the night watch. We're going to be positioning a camera with a special robot that has to maintain distance and facing to the painting within 130 micrometers of accuracy, because that's my depth of field. Anything that's outside of this little 130 micrometer, 2 human hair thick sliver of space will be too far away to be in focus or too close to be in focus. So I have a real-time 5-laser range-finding system and an artificial intelligence that helps me move the camera in real time to make sure that I'm getting sharp photos. So if this works, I will be happy. But it is rather insane to even try. I was also quite delighted to be invited to do imaging and data science for the Girl with a Pearl project. It's funny because one of the most commonly asked questions in the Rijksmuseum for visitors is, where's the Girl with a Pearl? And we have to say, well, it's not in the Rijksmuseum. It's in The Hague at the Mauritshuis. But still, this was a collaborative project between a number of different researchers as part of the Netherlands Institute for Conservation, Art and Science, NICAS. And what you're seeing here is another exploration of how to take extremely high resolution images of paintings. In this case, what we have is 9,300 separate 3D microscope photos that have been stitched together. But the reason that I'm choosing not to use a 3D microscope is, as you can probably see, there's a kind of grid here that's subtly visible, and that's because with the microscope we weren't able to get uniform lighting from the left and the right. This is the best I can do to correct that. But this is also 4.5 micrometer resolution image of this beautiful painting, which for scale, this is 40 centimeters wide, and this is 48 centimeters tall. So it's fun because you can see things like paintbrush bristles that are embedded in the paint. Retouches. Now, you might think, oh, this painting's in bad shape, but it's not. It's just that I'm looking so close. That this is very much like the objection that Hollywood actors have to high-def movies, is that suddenly every single tiny flaw is revealed. So can we go farther with a digital microscope? The answer is yes. We can go to 1.1 micrometer resolution. So this is 23,100 dpi. Again, the girl with the pearl. And what this lets me do is really look at the painterly technique. So you can see here there's a little dot on her lips here, another dot, and this dot that makes her lips appear nice and moist. And at this scale, I can easily identify the individual pigment particles. I can see here some cloudy varnish, and then I can see a retouch that's on top of that varnish. I can even vaguely make out the kind of shadow where the retouch is on top of the separating varnish. But now the problem, as I mentioned in my abstract, is that we go from a world in which we don't have enough data to one in which I'm now drowning in data. How can I possibly look at 768 billion pixels of the night watch? So the answer is, hopefully I don't have to, because I can train a neural network to identify the semantics of what it's seeing. And so in this case, with luck, yes. Here is a neural network that has been trained to identify the fibers that are present here. In this case, these are hair fibers or clothing fibers because the painting just collects these things. This was sitting face up, and so just floating around in the air, there's dust constantly, and when it settles, you get this kind of thing going on. And the reason for identifying fibers is because when I fuse this data with other data to try to figure out what the correspondence is between the chemistry and the 3D and the visible and the UV and everything else, I need to not consider the pixels that have fibers on them because the fibers move from one imaging technique to the other. So I have to discard them. But you can then imagine that I could also train the network to identify other things, and that will mean that I can basically have it spidering these 768 billion pixels, even though I don't have the time to do it. Yeah, so to give you some context here, if I would zoom in on this area of her turban, again, to convince you that this is not just some weird cult of resolution, that there is a good reason for doing this. Here's that same area, again at 1.1 micrometer, so 23,100 dpi. And you can see that if I zoom in at this resolution, I can actually see a place where the painting has lifted up a little bit on a crack, and then it's been chipped off. So I can see here a virtual painting cross-section. I can see a charcoal layer here, and I can see the ultramarine and the individual particles. Over here, I can see the varnish filling this crack, and I can see a bubble, a reflection in the bubble that's in the varnish in the crack. That's only maybe 10 micrometers wide. So it's a virtual microscope that provides on-demand access to any location in the painting. So setting aside high resolution for a moment, let's think about other ways to compare paintings. So on the right, you again see this copy of the Night Watch, which is only 80 centimeters wide. And here we see the actual Night Watch. This is out of its frame. This was taken quite recently because of the deframing that had to happen for our research campaign. And the question is, given that you see that there's more of the painting that's in the London's copy on the right, specifically this stuff over here and the top of the arch and so on, what is the correspondence? Was this actually painted after the Night Watch, or was it a copy that was made sort of from recollections, or what? So here, one of our conservators, Suzanne Smelt, has marked correspondences from one painting to the other to say, well, here's the tip of this spear, here's the tip of this spear, here's the pupil of this eyeball, and here's the pupil of that eyeball. And you can see that in a little behind-the-scenes view here. But the point is not that. The point is that with this correspondence between the 2 points, what I can do now is have a mode in which no matter where I put the mouse, it will align the 2 paintings semantically under the mouse so that I can really make a comparison. So for example, if I put it here, then I can bounce back and forth between the two. And you'll see that under the mouse, it's perfectly fixed. Or I can put it up here, and now he will be fixed. Or over here, and he's fixed. Or you can see that the extension of this guy's arm with his pike, or I'm not actually sure how to call that, a halberd, some kind of pole arm, is different between the two. So here I can focus on the halberd. Or I can put my mouse over here on his nose and I can focus on him. So you can imagine trying to play this game in Photoshop and then quitting after about 5 minutes out of frustration, I imagine. I certainly wouldn't have the patience to do it. We can, of course, fade from one to the other and so on. So it's actually interesting that what we learned from this is that, in fact, the copy is quite faithful in terms of the horizontal placement of the figures, but the vertical placement is what differs between the two. So you can see them moving up and down, but not moving left and right so much. So that does give us some confidence in the scale accuracy of the copy, and then this might allow us to imagine what the Night Watch looked like before it was cut down. It's known that it was cut down when it was moved from its original position into the Cloveniersdule in Amsterdam because it wouldn't fit between two doors. So they had to make it narrower and shorter because it just wouldn't fit in the room. And this was not uncommon to do in those days. So now we take a little detour into 3D things. So first, a kind of 2.5 dimensional thing. This is it's basically a sculpture in paint, right? So this is the sunflowers, which is in the Van Gogh Museum, also in the Museumplein in Amsterdam. And what you see here is a fusion of 8 photographs with the light at different positions. And so what you're seeing here is basically a virtual way to attach the light source to the mouse in real time. So some of you may be familiar with RTI, but this is not RTI. The math of RTI, in my opinion, is wrong, and the RTI viewer is not live streaming over the internet. So I'm not a fan of RTI personally, but I think the effect is more or less the same. You know, as you may know, when we photograph a painting, we usually do everything we can to flatten it, so that we get the color and all of the shadows that come from all these incredibly pastose areas are destroyed. But this is really intended to bring those out because there's so much beautiful texture that you experience when you're standing in front of a painting like this. So here, if I put the light source on the left, I can see all of the vertical brush strokes that are there in the pot from above. And I can see the horizontal brush strokes from below. Again, the horizontal brush strokes. So I'm moving the light source around. And in this case, in case you didn't notice it already, you can see here it says Vincent. So now an actual 3D object. This is a sculpture by Adrien de Vries. It's 1.2 meters tall. And Adrien de Vries is considered the sort of Michelangelo of the North. This was purchased at auction by the Rijksmuseum in 2015. And Taco Dibbits came to me and said, I want to find a way to present this to the public in a way that's never been done before. And I asked him what he had in mind, and he said, I don't know, that's your job. So, so this is a little behind-the-scenes look at what I came up with. So you may be familiar with a technique called photogrammetry. And with photogrammetry, you have a 3D object, and you take pictures of it from different angles, and you use this to reconstruct a 3D model of the object which you then would usually show to the public. Well, there are two problems with that. The first is that photogrammetry for glossy objects does not work, because when you're doing photogrammetry, you have to track how features are moving. But when you have a glossy object and you move the camera, you're mostly seeing a reflection of the light source. And the second is that so I used to write software for metal casting, and I have taught metal casting, and I know that the surface finish, the patina, is a huge part of what makes this object beautiful to look at. And so if I were to take a 3D model of this and present it to the world on the internet, I would strip it of almost all of its beauty, and so I won't do that. I would refuse to show 3D models and only ever show photographs of this object. But anyway, a little behind the scenes view is that I came up with a new way to do photogrammetry by combining photogrammetry with something that's called space carving. This is an intermediate view of the sculpture, sort of seen as being constructed out of little balls of clay here. This is in the middle of its process. You can see it's still not done. And what that gets me is a depth map. Again, this is the intermediate depth map. And so, in other words, light color here means far away. Dark color means close to me. And the punchline of all this is that now if I put my finger anywhere on the sculpture in this photo, I can tell you where that point is in space. So I have a 3D coordinate. All right. So if I do that with every photo I take of the object, then I can coordinate views of photos of this object in a way that's hopefully interesting. So here you see this one sculpture from 12 different views, equally spaced around the circle, so 30 degrees apart. And what this is doing is it's going to pay attention to the three-dimensionality of where I'm looking, so that whatever I put in the center of the screen in one window, it figures out, number one, where that point is in space. And then number two, it figures out where to find that point in space in all of the other photos, so that it can move to those other photos and show me the same point in space. So you can see here that if I bring this other hand into view, the different images will move, but in different directions, in order that now it's showing me that hand from all angles. Or if I take his head, now I can see the head from all angles simultaneously, which is a lot like what it's like to look at a sculpture. You behold the whole thing, you find an area that's interesting, you move in, and then you move around it and study the fine details, and then you go back out. So if I say, oh, that's an interesting pan flute, then here's the pan flute from every angle, including where it would appear here if it were in the front, because I still know where that 3D point appears in the photo. So another point of what I'm showing you is that I think it's important to respect not only human perceptual psychology, but principles of graphic design. So I'm not a big Apple fan, but I do respect Steve Jobs' approach to devices. He said that when you pick up an iPad or an iPhone, he wanted the user to have an emotional connection to the object. And I try to create an emotional connection to the art by getting out of the way. Hopefully you'll notice that there's no logos, there's no gizmos or sliders or home button or plus button or minus button, because these things all force context switching. These make you look away even if you're not realizing it. So I just want to get out of the way and let people look at the art. And that's a very intentional decision, hopefully to create an emotional connection, because I want people to come back and experience more of the art. Now, if temporarily we get a little bit more analytical, this will be brief, but hopefully interesting. When you have a painting on canvas, none of the Bosch paintings were on canvas, by the way, they were all on wooden panel, then it turns out that the pattern of spacings between the threads is a manufacturing defect, which is unique to that bolt of canvas. So here you have, side by side, the only full-length portraits that Rembrandt ever painted. These are 2.1 meters tall, Martin and Oppian. These were purchased jointly by the Dutch and the French from the Rothschild family a couple of years ago for 160 million euros. Yeah, that's a lot of money. This one is owned by the Rijksmuseum. Oppian is owned by the French, and by treaty they may never hang apart. These were a pendant pair of a newly married couple, and so they will spend 5 years in the Rijksmuseum, 5 years in the Louvre, and then bouncing back and forth 8 years apiece, ad infinitum. So we were responsible for doing the conservation treatment of these, and so naturally I did a canvas analysis. This is a new kind of canvas analysis. I'm sure if you've worked with Rick Johnson, you've also seen canvas analyses. This is a neural network-based canvas analysis that gives thread by thread tracking. So rather than the moving average that you may have seen before, this is every single thread. And you can see here, if I illustrate the spacing between the threads, here in millimeters, that the two have exactly the same pattern of spacings of their vertical threads. If I orient them foot of Oppian to foot of Martin. This is the spacing of the horizontal threads, so it looks like we've also got evidence that there is a shift change. So someone was working here, and then the shift changed, so maybe they slept and they came back much more energetic, or someone came back who was a lot stronger, and then when they were pulling the comb to pack the warp threads, they did so much more strongly for a little while, and then the shift changed again. So we can conclude that these were cut from the same roll of canvas, which was a question because it wasn't known whether these were really painted at the same time. And then if we look at the angles of the threads in this orientation, where you have the traditional pendant pair of the man on the left and the woman on the right, then we also have a little delight, which is that, so here I'm visualizing the angle between the horizontal and the vertical threads. And so what that means is that this is a single visualization that can show me cusping on all sides. So the idea is, in the 17th century, you would take a piece of canvas and you would take a wooden frame that was larger than the canvas. So this is not something we're going to wrap the canvas around. This is larger than the canvas. And then the canvas would be laced and stretched outward around this wooden frame with the lacing. And when you do this, it's as if I'm sort of pulling my shirt like this. You can see that the vertical threads of my shirt are going like this, where they're attached. And so down here you have that the vertical threads are at a fixed orientation and horizontal threads are going like this and cusping. So the angle between the threads is changing. And over here, the horizontal threads are fixed and the vertical threads are going like this. So as you can see, I have cusping on 3 sides of Martin, and I have cusping on 3 sides of Oppian, but I do not have cusping here, and I do not have cusping there. So this is evidence that these were, in fact, cut from the roll like this, and then turned and stitched to each other, and stretched and primed in this orientation. Whether they were painted together, we can't really say, although there is some evidence that they were not painted together, and that is coming from the differing vanishing points of the tiles here. You might expect that if they were painted together that you would paint one set of tiles and then paint them standing next to each other and later cut it, but the tiles don't have the same vanishing points. Doesn't prove anything because we don't know if these were the original depictions of the tiles. That's to be answered. But still, you can see that by applying a little bit of multi-scale material science, thinking of this as revealing the connection between processing and structure and properties, then we can say something about them as in an art historically interesting way. So I mentioned also that one of the techniques we're applying for the night watch is a technique called macro X-ray fluorescence. The idea here is that we perform X-ray fluorescence 101 million times over the span of 56 days over the night watch. And X-ray fluorescence, what it does basically is it takes a point on an object, we shine X-rays into it, the X-rays are absorbed by the electrons in the atoms, those electrons are promoted, leaving unoccupied states in the atom. Other electrons fall down from their higher energy states into those newly available lower energy states, and when they do that, falling down, energy is conserved and they give off X-rays. So the big picture is you put X-rays in, X-rays come out, and you detect the X-rays that come out, because the X-rays that come out have a characteristic energy depending upon the atom from which they have fluoresced. So this allows us, as you can see here, to detect a dizzying array of elements, anything that's heavier than aluminum, more or less. So this can be used to give us interesting insights about how the painting was painted. These are still preliminary results, I should caution, but I will still show you a bit. All right, so I am going to now show you, for the night watch, here I have the visible image of the painting. This is a map of the mercury, and here is a map of the arsenic, and over here is a map of the cobalt. So to begin with, the mercury is really easy to understand, because in a 17th century Dutch painting, mercury only appears in one pigment. So to back up a little bit, what makes this interesting and complicated is that painters don't paint with elements, they paint with pigments. And a pigment can have multiple elements in it, and any given element might appear in more than one pigment. So unfortunately, we don't have a pigment detector, we have an element detector, so we have to kind of unwind this whole thing. In the case of mercury, however, it's simple, because mercury appears only in mercury sulfide, which is from the mineral cinnabar, which ends up being vermilion. So where you see this image here lighting up, that's because Rembrandt used vermilion. And if you looked at 17th century Dutch painting practice, this is probably not a surprise. Sure enough, the vermilion colored things are painted with vermilion. And the skin tones, there's a lot of vermilion in the faces, for example. Now, cobalt and arsenic are also interesting and a little bit more complicated. So here, if I zoom in on the sock, you can see that from the rightmost image over here, that the sock is loaded with cobalt. And what cobalt would correspond to is also fairly straightforward in a 17th century Dutch painting. This is the pigment smalt. And smalt is made by taking blue cobalt glass, grinding it up into a powder and putting it in oil and painting with it. This does not say, however, that the night watch was originally blue, because smalt can be added to browns to make them more interesting. It's also often used as a drying agent so that you don't have to wait as long before you paint the next layer on top of that. So when you mine the cobalt ore, it always has an arsenic impurity. So where we see cobalt, we also see arsenic. All right. Not surprising there. So you see lots of smalt. But now if I go to the lieutenant, you'll notice something interesting has gone on here. Here's the arsenic, here's the cobalt. So here, in the trim of his jacket, you can see that there's a strong concentration of arsenic, but there's no cobalt there. So this is because arsenic can appear in more than one pigment. Arsenic appears in the pigment smalt because it rides along with the cobalt. Arsenic also appears in the pigments realgar and orpiment. Orpiment is particularly tantalizing possibility here because orpiment, which is arsenic sulfide, was used since medieval times. If you grind it up, it sparkles like gold. Unfortunately, in 15 or 20 years, it degrades and it becomes a sort of orangey yellow. It doesn't sparkle anymore. So there's a strong possibility, though we don't know yet, that the trim of the jacket was sparkly gold when Rembrandt painted the Night Watch. So again, we're still trying to analyze and make sense of all this, but you can see that this is now a lot of data. And if we try then to make more sense of that, here is a first attempt. This is now the same thing with Rembrandt's Jewish Bride. This is also in the Rijksmuseum. This is a painting that was Van Gogh's favorite portrait. He used to sit in the Rijksmuseum for hours on hours. He said he would give 10 years of his life to have 2 weeks alone with this painting. So it makes me feel a little bit guilty, but it's a beautiful picture. So what you're seeing here is the high resolution photo, and you can see it's really quite high resolution. In the upper left, you can see the radiograph of the painting. And I show this mainly to point out that this is really hard to interpret. You can see that mainly we take radiographs of paintings to show us the use of lead white and possibly concealed figures. You're also seeing the fact that this is a painting on canvas. So you see the wooden stretcher here. You see all the nails that are around the edges. And if you look carefully, you can also, assuming that the internet is actually working, you can also see some evidence of the canvas itself. Make sure that we're actually, yeah, we do have a live connection. And a weird development problem with the X-rays that make it look like this conceals a Gustav Klimt underneath. So we've done X-ray fluorescence. Actually, TU Delft did X-ray fluorescence, I believe. And let me show you then the live by the sword, die by the sword, I guess. This is going back to Amsterdam, which is apparently a bit fussy time to time. So here is the calcium map. Calcium is another nice example. This is very strongly associated with bone black. This is where you would grind up animal bones after putting them in the fire and paint with it. Could also be ivory black. So wherever you see dark shading, this is loaded with calcium. You can also see that the hat here is lighting up in the calcium. To nobody's surprise, probably. Now, if we look at iron, oops. Well, I accidentally clicked on mercury, but there's mercury, so that's vermilion. Again, not very surprising, I think. If we look at iron, iron is associated with earth pigments, so umbers and siennas and these kinds of things, ochres. And if you look in the iron map, it reveals that there was an earlier version of the hat. This is called the Jewish Bride, because this is a newly married couple that asked Rembrandt to paint them as Isaac and Rebekah from the Old Testament. And that's not something you could have seen using the radiograph. So now, again, I have this problem. Too much data. How do I figure it all out? So if I asked you the following question, I said, all right, I'm going to tell you that there's some chemistry at this point. I can't tell what's in front, what's in back, because when I do XRF, I can't tell you that. I just know it's in there somewhere. So let's, as an example, let's say I know that I have lead at some point. Then you might say, okay, that's probably lead white, so it's going to be white. If I tell you you have mercury, then you might say, okay, mercury, that's vermilion, so it's going to be reddish. So if I ask you the question, can you tell me the color of the painting if I only tell you the chemistry, then you might at first think, okay, I could do that. But what if I tell you that there's both lead and mercury at some point, and we don't know which is in front, which is in back? Can you tell me the color? You should probably tell me, no, that's a dumb question. Because now you don't know, is it vermilion on lead white, so it's red? Is it lead white on vermilion, so it's white? Or are they mixed together, so it's pink? You should say, it's impossible. However, if I tell you that this is painted by Rembrandt late in his career, then if you knew about how late Rembrandt painted, you might know that there are certain things he does and certain things he doesn't do. So that's what I've trained a neural network to do here. So this is, under the assumption that this is painted by late Rembrandt, a computer's best guess about the color of the painting from only the chemistry. So the actual painting is here, the computer's guess is there, and it's always interesting when you make a model like this to find the places where it's wrong. And as you can see here, it apparently thinks that she has an unfortunate skin condition, these black dots on her face. So why did the model get the wrong answer? Well, hint is here in the calcium map. You can see the calcium map is lighting up in calcium. So at the risk of anthropomorphizing a computer algorithm, a neural network, the computer thinks when it sees this high concentration of calcium that this is bone black, and because it's so concentrated, it thinks that it's in the front. So it's thinking, this is bone black, therefore this should be black areas. But remember, this prediction is based on the assumption that it was painted by late Rembrandt, or that it's painted as late Rembrandt painted. And so, in fact, it gets the wrong answer because the assumption that it was painted by late Rembrandt in those areas is wrong. These are retouches. As you can see here, these dots. And one of the techniques that painting conservators use when they have a paint chip that's missing is they'll fill it with gypsum and then paint over it, and gypsum is also rich in calcium. So in other words, I have here a neural network that makes the right prediction about its color where it is painted as late Rembrandt painted, and gives the wrong answer where it is not painted as late Rembrandt painted. Late Rembrandt doesn't use layers of gypsum and paint on top of it, so that's why it got the wrong answer there. So you can imagine that this is a potentially very exciting way to perform analyses that give us additional evidence for use in authentication. At the risk of breaking the flow, I forgot this other 3D object. This is a movie that I was asked to create for the opening of the exhibition on the Kwab style. This is the Vianen ewer. This is said by the curator, Rainier Barson, to be the most important object in the Rijksmuseum. This is the epitome of style in the time of Rembrandt. This is an object that's made of a single piece of silver, at least without the lid, by Adrian van Vianen. It's been depicted more than 70 times in Golden Age paintings. And here I was asked to make this 5-meter wide opening movie for the exhibition that featured this thing. And we had time to take photos that were 1 degree apart. But in order to make this nice and smooth, I needed photos that were 1/4 of a degree apart. So I had to train a neural network to imagine 3 out of 4 photos as if I had taken them. So imagine that I show you the 1 degree photo and the 3 degree photo, and I say, could you imagine the 2 degree photo? The one that was rotated by 2 degrees? Yeah, you could probably do that because you know what the object looks like. Or if I showed you the 4 degree photo and the 6 degree photo, and I asked you to imagine the 5 degree photo, you could probably do that. So here I trained a neural network to do that. I had 1 degree photos So I asked it to imagine the photos that would have been taken between those. So then I had half-degree photos. And then I further asked it to imagine what would have been between those. So I had 1/4 degree photos. So this is smooth, but only 1/4 of these photos were actually taken with a camera, and the rest were imagined by a neural network whose job it is to be good at imagining photos at intermediate angles. So people who looked at the movie in the opening of the exhibition probably didn't think that this is a very data science-y kind of thing. It just looks like a movie, but it's actually 76 gigabytes worth of photos turned into something like 300 gigabytes worth of photos, because we didn't have a robot to fly into this thing. We just had to take photos from different angles and then simulate flying into it. But these are all photos, except for the ones that are just imagined by a neural network to be like photos. Yes. So, how am I on time? Okay. Then what I will do is, very quickly, I've been zooming into objects, and now I would like to zoom out and to put the object in context. So very quickly, this is a painting by Bosch, and this is another way of experiencing the painting in which whatever I put at the center of the view, here I put a barrel. This is every barrel from the entire oeuvre of Bosch that's been automatically extracted and sorted according to the similarity of what is on the screen. So you can see this updates itself as I move around. So if I put a ball on a string in the center, here's all the balls in a string in all of Bosch. If I click on one of those, these are hot links, so I can go to that particular ball in a string in this particular Bosch painting, which is a real favorite. Of course, this is the Garden of Earthly Delights. And then this is every painting, 4,750 paintings in the Rijksmuseum at full resolution, which have been organized semantically by a deep neural network. So the idea is, with no metadata whatsoever, with only images going into this artificial intelligence, I have designed an algorithm so that if two paintings are viewed as being semantically similar, yeah, so you can see they're all at full resolution, then they'll be near each other. So over here you have still lives, floral still lives. And then over here I have still lives with fruit and food, and then game animals, lobsters, and pheasants, and so on. And then over here I just have just dead animals, and then dead people. Or to give you a sense of what this is doing, if I can find it, yeah, I think it's here. So here is the woman reading a letter. And so here you can see this is a woman facing a window, holding a letter, head tilted downward, with a chair in view, with her hair tied up in a certain way. And it puts it next to this. Again, a woman holding something, arms bent, facing a window, with a chair in view, head tilted down. And also this. So I didn't have to put in any metadata whatsoever. It just decided that these belong together. You can see here it does militia company portraits. There's the night watch and the copy, which it's correctly put near each other. Here I have a militia company. Where am I? I'm lost a bit. Oh yeah, a militia company with their dog, and then people with their dogs, and then just dogs, and groups of dogs, people on horses, groups of horses, farm animals, groups of farm animals, and so on. So it's basically a way to organize the entire collection of paintings in a smooth semantic gradient. And so I will finish with, literally and figuratively, the big picture. This is every work on paper in the entire Rijksmuseum. 177,000 images organized using the same technique and also at full resolution. This image is 1 million pixels wide and 768,000 pixels tall. So this is the same size as the single image of the Night Watch that we hope to be creating in the next few months. This was made with no metadata and images only. And so you can see that the neural network thinks that self-portraits of Rembrandt belong together. That it thinks farm animals belong together, horned animals, standing animals, laying down animals. Over here we have ships of all varieties, and so on. The big picture, I hope I've convinced you that we're just at the beginning, that by combining the latest in high-resolution imaging technology, data fusion, material science and engineering, and perceptual psychology to help us have the technology get out of the way, that we can help the world to access, preserve, and understand its cultural heritage. Thank you.
We all stand absolutely dazzled by the pyrotechnics of digital technology. I think we have a few moments, for questions. I'm happy to open the floor to questions.
When you do OCT on painting, I mean, my understanding of OCT is that you're looking at layers of points of disjunction, basically.
Yep.
But what are you looking for from that data? What do you hope to gain from it?
So OCT is optical coherence tomography, and it's kind of like sonar with light, essentially. So it is capable of telling us the thickness of all of the translucent layers, so we'll be able to see how many layers of varnish there are on the Night Watch. It's been restored at least 25 times that we know of, and of course, now when we restore a painting, we take off the old varnish and we put on the new, but we know that it's not going to be a single layer of varnish at the moment. It's also, by looking at the decay of the signal, able to tell us scattering and absorption coefficients. So we can imagine that we would have a map across the entire painting of things like the thickness of the varnish, the number of layers of varnish, the transparency, the scattering or the translucency, the absorption coefficient of the varnish across the whole painting, so that we'll have some idea in the future of being able to make physical models that will allow us to predict the appearance of the painting with a varnish removal before we actually do it.
I have an art historical question. I mean, first, this is dazzling and wonderful and thrilling and wow. That's not the question, but fantastic. Thank you. I was thinking about your scans and photographs of the girl with Pearl, and wondering if your research might help settle one of the questions in Vermeer's scholarship. You know, it's sort of a cliche of the work on art historical writing about Vermeer that he painted as if he were an impressionist. He was trying to capture a purely optical image, that he was perhaps working with some kind of a screen and just picking up dots of light or patches of color without painting contours as painters habitually do. It struck me in your photographs that at moments one saw highly directional brushstrokes. So I wondered whether your work on this has led you to some insights into the question of to what extent does Vermeer's brushwork follow contours versus to what extent does it seem to be capturing purely optical experience?
That is an excellent and fascinating question, and I wish I had had time to study it. So I was just one member of the team here, and these images were collected by Emilian Leonhardt, who works for Hyrox. They're the makers of the microscope. And I fused the data together, and I moved on to the next thing because I was basically providing tools for others, and I have 43 active projects. So I think that the question is partially answered by what you see here, but it's difficult to make a direct assessment because our perception is strongly dependent upon the scale at which we're doing the perceiving. And so as I'm zoomed in here, this is not what you perceive, of course. And so I think in order for the computer to add more than just a virtual way to look at the painting, we would have to do some more research on the connection between scale and perception to know. I mean, yeah, I'm familiar with the various theories that he used a lens and so on, and you do see transitions, for example, on a woman reading a letter between the blue of her dress and the white of the background that suggests that there are chromatic aberrations that he actually painted because he was looking through a lens. I know these theories are quite controversial, but ultimately, beyond high-resolution images, I'm not sure how I can answer.
Thank you.
Yes.
Thank you for this absolutely fascinating presentation. Worlds were opening up. I've got more of a practical question. Wondering for whom exactly this information is, like who will be able to access this information? Is it for scholars? Is it for conservation? And then is the idea that, or is it going to be online? Is it a paid service that I can access? Is it a program that I have to install? Like where's that data, that immense amount of data being stored? And then is the idea that every museum, because it sounds like it's a 10-year project that you've been doing with the Rijksmuseum in a very large team, is the idea that every museum in the future will try to have such a service?
Yeah, that's a deep and very good question. So to clarify, my 10-year project is just before we really get heavy with using material science to understand paintings, we have to have a set of computational and imaging infrastructure with which we can manipulate these things. And so I have a 10-year project to try to build that. But this started before I joined the Rijksmuseum, and my position at the Rijksmuseum is permanent, so it's not like I'm about to leave or something like that. So when you talk about this data, the thing is that the data comes from museums all over the place. So the short answer is the curtain viewer is made with an intent that it be open source. It's not open source yet because it's not robust enough for people to use it. I should say that the curtain viewer is like, using the curtain viewer is 2% of the work when you have new images. 98% of the work is getting everything so that it's carefully stitched and registered, and that even though these images are dramatically different resolution, that you can switch from one to the other without having misalignments. And so the stitching and registration technology is the really, really hard part, and that's still under active development. The curtain viewer is just, if you happen to have images then that are aligned, then you can use that easily. The Bosch project was made by me. That whole website was exclusively my work as an attempt to show what's possible with a small budget, because I pay for the whole thing. I was not funded in any way to make the Bosch project website, and it costs me 12 euros a month to host. It's out of the cloud. There's 14 terabytes of data, but that's not a lot in terms of cloud storage costs and so on. So the Bosch project website is my attempt to show what's possible with a low budget. In some cases, the Rijksmuseum, I came to work at the Rijksmuseum because of the philosophy that every piece of data we collect will ultimately be free for the public to use for whatever they want. So their openness with digital things was a huge attraction for me. But of course, it's on a case-by-case basis, with some museums who make their revenue by licensing images. I can't put it online for everyone to use. But in the case of the Bosch project, we were able to get the museums to agree to that. But that's because I'm not selling the images, and you can't just download a huge Bosch image off the Bosch project website. You can only view it. So the big picture is that I think that there's momentum towards being more and more open. Of course, now the Met has all its images online, and that's incredibly encouraging. But some places like the Louvre, it's probably not going to happen in any foreseeable future because they have a much different view of copyright and ownership and so on. So, yeah, hopefully the museums that are behind will get dragged along in the future. But this is more trying to show what is possible with simple infrastructure and not a lot of money. I realize that not everyone can spend 3 million euros on the kind of project that we're doing with the Night Watch. But what I'm doing is supposed to be a mix of what hopefully everyone will be doing in 5 or 10 years on one end of the spectrum with something that anyone can do at home on the other end. So trying to chart the whole path.
I was curious if you could talk a bit about how you train these neural networks, and particularly if you've found any semantic biases in doing so, and then recursively, whether that teaches us something about the way we look at art.
Yeah, I probably have tonight talked about 5 or 6 different kinds of neural networks. So if you mean the one at the end where I'm comparing the paintings and so on, I didn't actually train that neural network at all. This was, in fact, an experiment to see whether or not existing trained networks off the shelf, in this case from Google, but you can get one from Microsoft, you can get one from Facebook, Google, Amazon. They all have pre-trained networks to solve the problem called ImageNet, or the International Large-Scale Visual Recognition Challenge, ILSVRC. This is an annual competition to classify images, and the idea is you show the computer an image and it says, oh, that's a fire engine, or that's a bookshelf. And so I reasoned that by taking such a network that was good at that problem, cutting off the head, in which it's telling me that it's a bookshelf or a cat, and looking at the inputs that would go into that, so the second to the last layer in the network, that those neuron activations would contain strong semantic content. And so I have 2,048 numbers for every single image in the collection, and the algorithm here takes 2 images and puts them near each other if those 2,048 numbers are the same or similar. Those 2,048 numbers I hypothesized were expressing semantic content, and the result is, to me, convincing. But as to bias, I'm not sure how I would check. It is an important question, certainly. I don't see what I consider to be bias, but it is true, for example, that depictions of one gender are placed together and depictions of another gender are placed somewhere else. And these are, the collection of the Rijksmuseum, so it's mostly 17th century Dutch art. So it could be a lot to do with dress, headwear, and things like this. But beyond that, I'm not sure how I would check.
I think actually the time is up. I think if you're willing to take a few informal questions after, but I think in the interest of time, I will just say you've clearly, I think, raised in your work extraordinary questions for both the practice of conservation and for the understanding of art from an art historical point of view. Thank you so much for.